So welcome to the section 2.1 particles revision video. It's quite a long video, this one. It's about an hour and 40 minutes, but you can always do it in chunks and stop halfway through, but you're likely to need quite a lot of free time. You're almost certainly going to need a sheet of A3 paper for this one. It's quite a lot of information, and I'll be using 4 colours of pen, so I would get those as well. A few other things you might need. Copy the formula sheet to see exactly what you're given in terms of baryon numbers and so on, and also a copy of the textbook or revision guide and your particles physics booklet and notes. Once you're ready, move on and enjoy. So the first bit of the particles topic that you did in the lesson was on the constituents of the atom. And you knew a lot of this from GCSE, so it's quite a nice way to start the topic. And you know that the traditional model of the atom has a nucleus containing positive protons and neutral neutrons. And you also know that around the outside orbit electrons in certain specific energy levels. And you might have drawn something like that in chemistry. So what you need to know for physics is the charge of these particles. And the charge of an electron is on the formula sheet actually, and it could be written as minus E, minus charge on electron, or minus 1.6 times 10 to the minus 19 coulombs. Usually we measure charge in coulombs. The proton is plus E, or plus 1.6 times 10 to the minus 19 coulombs, and the neutron is obviously neutral. You can look up the masses of these on the formula sheets as well, and the mass of a proton, I'm running out of space here, mass of a proton is 1.67 times 10 to the minus 27 kilograms, which is a really, really small mass. And the mass of the proton, mass of the neutron is almost the same. It is in fact slightly heavier, but not to 3 significant figures. So mass of the proton, mass of the neutron are about the same size. The neutron is slightly heavier, and they are really, really, really tiny. However, the electron is even smaller than that. The mass of an electron is 9.11 times 10 to the minus 31 kilos, which is nearly 2,000 times smaller. It's very small indeed. But all of that is on the formula sheet. One thing to note, in the upper sixth, you will find that when you put protons and neutrons into the nucleus, their mass changes. So be wary of that next year. And that's where the energy for fusion and fission comes from. So some other things you need to know from this lesson, besides the particles in the nucleus and be able to look up their masses and charges off the formula sheet, is the concept of specific charge. Now, specific charge is something that's measured in coulombs per kilogram. And if you look at the unit that's given, on, it's very often given at the end of the question, it will say calculate the specific charge, and it will leave a line for the answer with C kg to the minus 1 at the end. That tells you how to calculate it. It's the charge in coulombs divided by the mass in kilos. Now, a few little things to watch out for. They may well say calculate the charge, specific charge on a nucleus, in which case the mass is the total mass of the nucleus, mass of protons plus mass of neutrons, and the charge is the charge of all the protons put together. However, they might also say, calculate the charge on an ion. Now, if you've got an ion, you've either removed or added electrons. So you have to look very carefully. If they say they've removed 2 electrons, the charge is just going to be 2 lots of the electron charge, which is down here. So that's going to be charge on an electron multiplied by the number of electrons that have been added or removed. The mass obviously will be the mass of the whole thing. Usually in specific charge calculations, you can ignore the mass of the electron because it is so small, it won't affect the third significant figure of your calculation. So that's specific charge. You were reminded of the notation for writing nuclides down, which is you have some nuclide X, which could be C for carbon, it could be H for hydrogen, He for helium, O for oxygen, and so on. And then you've got a number at the top, which is A, and a number at the bottom, which is Z. This is called the atomic mass number, or just the mass number. And it is the number of protons plus the number of neutrons in the nuclide. And the bottom is the atomic or proton number, which is the number of protons in the nuclide. And the final thing you need to know from this lesson, which I shall squeeze in just here, is what an isotope is, and that was covered at GCSE, so hopefully you are fairly familiar with it. It comes from 2 words, iso, meaning same, and the word tope comes from topos, meaning place, and isotopes are found in the same place as the periodic table. So you could have several isotopes of carbon, but they're all carbon, so they all occupy the same space in the periodic table. What are they? Well, they have the same number of protons, but different numbers of neutrons. And when we talk about isotopes, we generally refer to the nucleus, and we don't worry too much about the electrons. If it's got, they'll all have the same number of electrons. They have the same number of electrons as protons orbiting around the outside. It's just the neutrons that are different, which makes them slightly heavier or slightly lighter. And if you've got an isotope, usually it's less stable. Well, different isotopes. One is a stable isotope, and the rest of them are usually unstable and radioactive, but it does depend on the specific elements that you're looking at. So that's the end of lesson 1. In the second lesson, I got you to watch a video on the neutrino. Unfortunately, it's been removed from YouTube. It was a Horizon documentary, a very good Horizon documentary that talked about and introduced you to this idea that protons, neutrons, and electrons are not all there are in the universe. There's actually many other particles. And the video told you the following about the neutrino: that it has no charge, and originally they thought it has no mass. But actually it turns out that it doesn't travel at the speed of light, so it has a very small non-zero mass. Has a very small mass. As it doesn't travel at the speed of light. You don't need to know that's the reason, but the video did a very good job of talking about the fact that actually neutrinos change from one type into another, and we'll talk about the different types of neutrino in a little bit. But because it changes, it must experience time, and if it experiences time, it can't be traveling at the speed of light, because things that travel at the speed of light, time slows down and stops, which is special relativity. It's really interesting, but it's not on the course. I can recommend some books if you come and find me on it. So we know it's got a very small mass. And we also know from the video that it comes in 3 flavors. There are 3 types. There is the electron neutrino. It's given the symbol nu, the Greek letter nu for neutrino. which is like a V, but it's kind of a curly V. So there's an electron neutrino. There's a muon neutrino, whatever a muon is. We'll come to that later on. And there was a tau neutrino. So there we go. 3 flavors of neutrino. And the reason that they discovered it was in beta decay. Now in beta decay, as you might remember from GCSE, a neutron, which is neutral, no charge, changes into a proton and an electron. Now that's good because we started off with a neutral thing afterwards, and afterwards we had a positive and a negative, and overall it was neutral afterwards. However, when they measured the energy of the electrons, they were all different. You had electrons flying off with really high energies or really small energies, but there was a maximum. And they went, well, this is really odd because in each decay, the same amount of energy is released. The nucleus is doing the same thing. It's changing a neutron into a proton. That releases the same amount of energy each time. So why is it the electrons all have different amounts of energy? Because the electrons carry it away with their kinetic energy. And they theorized that there must be this other particle, the neutrino, which is carrying away the energy. Now, in beta decay, for reasons we'll get onto, that happens to be something called an antineutrino, but more on that later on, and we write that with a little bar over the top. So it was as well as the charge being the same before and after, energy had to be the same before and after. Energy had to be conserved, and it was the fact that it wasn't, or didn't appear to be, that made them predict this extra particle. We'll come back and add some more to this later on. Moving on, the next chunk of the course, part 3, was called stable, or entitled Stable and Unstable Nuclei. And we started off by looking at a bit of a problem that should have bugged you at GCSE. And we said, well, supposing you've got a nucleus full of protons. Well, all the protons should repel each other and the whole thing should fly apart. So why doesn't it? Well, there must be another force pulling it together. And that force is called the strong force, which pulls protons and neutrons together in the nucleus. It does a number of other things as well, which we'll cover a little bit later on. And you need to know a little bit about how it varies with distance. So, imagine this is distance from, let's supposing here we've got a neutron, and then we've got position another neutron at various different distances along, away from this first neutron. And then we're going to have the strength of the force. And this force is very, very strong. So actually, it's on the order of kilonewtons, which is absolutely massive. If you're about 70 kilos, which is average, then the force gravity exerts on you is 700 newtons. It's, this is on the order of 10 times larger, and it's not a force exerted on you, it's a force exerted on tiny, tiny little particles, protons and neutrons in the nucleus, times 10 to the minus 27 kilos, ridiculously small masses. So this force is really very, very strong indeed, hence its name. Now, the strong force doesn't always act in the same direction. There we go. So that's what it looks like. And beyond about, this is measured in femtometers, so these are really, really small distances it acts over. Beyond about 3 femtometers, the force is 0. And below about 0.5 of a femtometer, something different happens. Now, if we define a positive distance to be moving away, then a positive force will be repulsive, moving or pushing something away. So positive is away in this diagram, and therefore a positive force pushes things away. It's repulsive. And the negative force here is attractive. So if two protons or neutrons are somewhere between 0.5 and 3 femtometers apart, there is an attractive force, strong force, between them, holding them together. The exam board do expect you to know those distances of about 0.5 and 0.3 femtometers. If you look them up, they're only approximate. If you look them up online, you might see slightly different values, but those are the values the exam board quote. To give you an idea of the size of this, that maximum attractive force is about 25 kilonewtons, 25,000 newtons down the bottom there. Why did we look at neutrons here? Well, that way we only have to deal with the force between two neutrons, and we don't have to deal, if we had, two protons, we would be experiencing the repulsive electrostatic force between the two, and that would make it very difficult to distinguish between that force and the strong force. But the strong force does exist between protons and neutrons, well, all protons and neutrons. The other thing that you covered in this lesson, besides looking at the strong force, was also equations for radioactive decay. So if you have slightly too many neutrons, for example, or slightly too few neutrons in a nucleus, then it becomes unstable and it tries to either get rid of some neutrons or gain some neutrons from somewhere by converting neutrons, for example, in beta decay, into protons if it's got too many neutrons for the number of protons that it has. There's a bit more information on this later on in this module, and there's yet more in the upper sixth when we look at why that number of neutrons to protons is so crucial. So let's have a look at beta decay. So we've done it already. We said a neutron decays into a proton. And the way we'd write this out is we'd say, right, imagine we started with some element X. Doesn't matter what it is. And it has some atomic mass number A and atomic number or proton number Z. And when it decays, it changes into a second nucleus, which we'll call Y. And that has atomic mass number A and a proton number. Because a neutron has changed into a proton, we've gained a proton. Now we've lost a neutron but gained a proton, so A doesn't change. Lost one neutron but gained one proton. And we get left with the electron or beta particle, which we could write with the beta symbol, and this weird particle, the electron antineutrino, which we'll put in there. Now, you could write that beta symbol as an electron, but what's the difference? Well, a beta particle, beta radiation, is an electron that's moving at very, very high energies. That's what makes it so dangerous. Normal electrons, you've got loads of normal electrons in your body, billions of them. Not dangerous because they're not moving very, very quickly. Beta particles, very dangerous because they have a lot of energy. In a bit like, I suppose, if you had a machine gun and you fired it at a wall, once the bullets are embedded in the wall, they've stopped, they have no energy, and they're not dangerous anymore. In the same way as, electrons that aren't moving very quickly aren't very dangerous. Now, what numbers do we put on a beta particle? Well, it's got an atomic mass number of 0. It contains no protons and no neutrons, and it's so much smaller than the proton and neutron, its mass is essentially 0 in comparison. But what about the proton or proton number at the bottom? Well, we write that as -1, and that way the numbers at the bottom join together. Now, why would we write that as -1? Well, because if you have a proton, one proton, and then you add an electron, they can go back together again and form a neutron in something called electron capture that we'll cover in a little bit in a couple of lessons' time. So that -1 is written on the bottom there for the beta particle or the electron. Let's just remind ourselves that this is in fact an electron. And that's how you would write beta decay. We also covered alpha decay. And we use a similar notation to this. Let's just put a red box around this one. And again, we start off with some nucleus X. But this time, we don't change neutrons into protons, we do something else. And for that, you need to remember what an alpha particle is from your GCSE. It's going to change into some other nucleus, Y, and we'll look at the numbers in a minute. And we're going to have an alpha particle. Now, an alpha particle consists of 2 protons and 2 neutrons. It's a helium nucleus. No electrons, just 2 protons and 2 neutrons. So the total number of protons is 2, and the total number of protons plus neutrons is 4. Therefore, if we lose an alpha particle from nucleus X, we lose 2 protons and 4 particles from the nucleus. Let's rewrite that, make it a bit clearer. And that's what happens. Now in the exam, they might give you a starting nucleus, for example, uranium-235, and they might give you a decay chain. They might say, well, it decays via alpha, beta, beta, alpha, or whatever. And they'd expect you to be able to go through all of those decays, work out how many protons and neutrons you lost or gained in each of those decays, and then work out what element you'll have, how many protons and neutrons you'll have in the element at the end. You won't be expected to memorize how many protons and neutrons there are in everything in the periodic table. That just isn't going to happen. But there might be clues in the question. I've seen questions before where they've done, say, 2 alpha decays, where you lose 2 protons, and then 2 beta decays, where you convert 2 neutrons into 2 protons, and you end up with, if you lose 2 protons and gain 2 protons, you end up with the same element that you started with. And then you would be expected to realize that therefore it was going to be the same as the element, whatever element they'd given you at the start, and writing the appropriate element symbol. The only thing we haven't talked about is gamma. Now, gamma radiation is high energy. It's a high energy EM wave. By EM, I mean electromagnetic. High energy electromagnetic wave. And therefore it has a high frequency as well. Goes up and down, the wave goes up and down many times a second, really, really high energy. Now, that happens if, let's say, you have another kind of decay, and then you end up with the positions of the neutrons and protons aren't stable anymore. They were stable in the they were in the right energy levels in the previous state, but then when you change a neutron to proton, or you remove 2 protons and neutrons, the remaining ones may have to drop down into lower energy levels, a bit like when electrons drop down energy levels in an atom, and then they release energy, and that's a gamma photon. So there we go. We should show that that's referring to that. And that's the end of stable and unstable nuclei. So the next bit was on photons and photon energy. Now you will have been taught this with the particle section, not the particle section, with the EM and quantum section that we taught you first, because you needed this knowledge to be able to look at the photoelectric effect. So it won't be in your stable, it won't be in your particles booklet, it'll be in your other one, but we'll include it here for completeness. And you know from the waves topic that light behaves like a wave, because we looked at Young's double slits. Don't draw this. But a quick recap, we looked at Young's double slits and the waves spread out, and we had patterns of light, dark, dark on the screen. In other words, you got interference. You got the two waves interfering constructively and then completely cancelling out. And you can't have a particle and a particle making no particle. So that's evidence of wave-like behavior. So light behaves like a wave, but it also behaves as a particle. And the evidence for this was from the photoelectric effect. The idea that the electrons in the surface of metal can't continuously absorb energy. They can only absorb a single discrete lump of it. And if that lump is large in the energy and they need to escape the work function, they can escape from the metal and the metal will discharge. They can't absorb a continuous amount. They can't keep absorbing energy. Light comes in lumps. It can only be absorbed in lumps, and those lumps are the particles, and we call them photons. A photon is a particle of light. Now you need to know the formula. We know that energy is proportional to frequency. In other words, if you double the frequency of the light, then you double the energy. And you can do that with the photoelectric effect. You can double the frequency of the light. You can work out how much energy it takes to release the electrons from the surface. So you know that, and then you can work out how much kinetic energy you've got from the electrons. And from there, if you double the frequency, you work out that you've actually got twice the energy of these things. And the constant that links the two is this thing h, which is called Planck's constant. Which you can look up on the formula sheet, but it's 6.63 times 10 to the minus 34. Units, well, if we rearrange, we get h is E over F, and frequency is 1 over time period, which is E over 1 over the time period. Don't write this down, which is energy times the time for one wave, which is measured in, energy is measured in joules, and time is measured in seconds. So the unit of Planck's constant is joules times seconds. Therefore, it's really important that you make sure that your energies are measured in joules before you use this formula. Now we can combine this with the formula V equals F lambda, or C equals F lambda, where C is the speed of light. And then if we rearrange that, for F we get C divided by lambda, so we can have a slightly different version of this formula, like that. And this is quite an amazing formula because it links a particle-like property, which is the energy of a photon. You can't have less than that amount of energy. You can't deliver less, and you cannot deliver, say, 1.5 amounts of that, 1.5 amounts of the photon energy. Energy comes in particles called photons, and you can only deposit an amount of energy equal to a certain number of photons onto the surface. You can't have you can't deposit any amount of energy. You have to deposit 1 photon's worth of energy, 2, 3, 10, a billion photons worth of energy, and so on. So it links a particle property with a wave property, such as frequency or wavelength. So a kind of question they might ask you on this, they could tie in with some stuff that you'd learnt in other parts of the course. So here's an example, power of a laser. And power is energy per second, so you're expected to know that from mechanics. And if we know that we have, let's say, each photon has an energy of hf, then the total amount of energy per second that must be deposited must be hf multiplied by the number of photons per second. Probably shouldn't really box this because this is just an application of a previous formula. It's not a new one. And you shouldn't try and memorize it, but it should be common sense to you. If you have a photon, let's say, with 10 electron volts worth of energy, and if your laser is emitting 100 photons every second, the total energy per second is going to be 100 lots of 10, or 1,000 electron volts every second. And that's what that formula is saying. A quick reminder on electron volts, although that is covered in the quantum mechanics part of the course. So if you have 1 volt between 2 plates with a voltmeter, which means that every coulomb gets 1 joule. If you move a coulomb, 1 coulomb, don't draw this, I'm going to rub it out in a second. 1 coulomb from one side of the plate to the other side of the plate, it's moved across 1 volt, so it's gained 1 joule of energy. And that's fine, that's how we deal with electrical circuits. However, if you move an electron from one plate to another, it doesn't gain a whole joule of energy because an electron is a very small amount of charge. So the energy, remember voltage is energy per coulomb, so therefore energy is charge times voltage, which is 1.6 times 10 to the minus 19 multiplied by 1 volt. So that means that the energy that the electron gains is 1.6 times 10 to the minus 19 joules. In other words, supposing we didn't have an electron, let's supposing we had a 2 plus ion. Let's say we had, it would be moving in the opposite direction. Let's supposing we had an Fe 2 plus ion suspended in some liquid, say. Now there, we use the red for the positive charge. Charge is now 2 lots of 1.6 times 10 to the minus 19, but it's still moving through 1 volt. Whoops. 1 volt. So now the energy that we have is 2 lots of 1.6 times 10 to the minus 19 joules, or 3.2 times 10 to the minus 19 joules. This is a bit of a faff, so it's much easier to call this 1 electron volt. It's the energy gained by 1 electron when it moves through 1 volt. You could get it using the same formula, but if this is in charges, units of electron charge. In other words, instead of writing a charge of 1.6, you write a charge of 1. Instead of writing 1.6 times 10 to the minus 19, you write a charge of 1. That's still in volts. Then the energy will be in electron volts. So let's just redo those examples. So the first one, E equals 1 times 1 is 1 electron volt. That's for our electron. And for our 2 plus ion, charge of 2 multiplied by 1 volt gives us 2 electron volts. And it's a much more convenient number. So that's a quick reminder on that. But remember, whenever you use Planck's constant, it is measured in joule seconds. So your energy must be in joules, otherwise it won't work. Okay, that's the end of that section. So section 5, that is on particles and antiparticles. Let's see where we can squeeze this in. Particles and antiparticles. And this is really very weird. The idea that you can have a particle and you can bring another particle, its counterpart, the antiparticle, and you can bring them together and they both disappear completely and change into energy. So here's an example. We have a particle and we have its antiparticle over here. Now this could be an electron and an anti-electron called a positron, or it could be a proton and an antiproton, or it could be a neutron anti, it could be anything. And it converts itself into energy. Now, we're not going to look or talk about why it does that, but it does. It's an observation that physicists have made. And the amount of energy released is given by Einstein's formula, E equals mc squared. And we'll look at that in a second. But what makes an antiparticle an antiparticle? Well, it has the same mass as a particle, but it has a different charge. So an anti-electron would be positive rather than negative. It also has a different lepton number, baryon number, and strangeness. In other words, if you have a particle with a lepton number of 1, its antiparticle would have a lepton number of -1. And we'll look at lepton numbers, baryon numbers, charges, and strangeness in the final lesson of this module. But for the moment, when you come across those terms, remember that if a particle has a positive lepton number, an antiparticle will have a negative lepton number. And so you need to take this into account. Antiparticles and particles, particle plus antiparticle, they're written with a little bar over the top. Annihilate and turn into energy. Okay, become energy. Now, when you have an annihilation, you have to produce 2 photons in that annihilation, because photons have momentum. So you must have 2 photons moving in opposite directions to ensure momentum is conserved. Otherwise, you've got a photon moving in one direction, but nothing to go in the other direction to counter it out. So energy of a photon is HF. Photon 1, energy of photon 2, like so. Now, you would have a particle over here with a mass of m. You'd have an antiparticle with the same mass m. So the energy you get from annihilating those 2 particles would be as follows. Energy released equals m times c squared for the mass of the particle, plus another mc squared for the mass of the antiparticle, gives you 2 m. Strictly speaking, these should be something called m naught. It's called the rest mass. And that's the total energy. We'll come back to what's called the rest mass in a second. That's the total energy that's been released from this event. Now that is given, total energy released, given to 2 photons. So energy of 1 photon is half the energy released, which is equal to E photon. Actually, let's just write it underneath. Equals m naught c squared. So each one of those photons will have the energy of one of those particles. But in the exam, you must show that you realize that it's the mass of both particles that's been annihilated. So you have to do that calculation to work out two lots of the mass of the particle. In other words, the mass of the particle and the mass of the antiparticle. And then divide it by 2 to show that you realize you've got two photons. Failure to do that will not get you awarded the marks. So this is annihilation. So why is it called the rest mass? Well, if it's going quickly, if the particle has kinetic energy because it's moving quickly, then E equals mc squared tells you that its mass has increased. Increase in mass, which we'll call delta M, would be the kinetic energy divided by c squared. So it's going to be really, really small for the most part. C squared is a massive number. But if you're looking at a particle that's very small, like an electron, this can be quite considerable. And actually, as you approach the speed of light, relativity says that the mass of something becomes bigger and bigger and tends to become infinite, which is why you can't travel faster than the speed of light, because you just get more and more, you get infinitely massive, and you can't accelerate to the speed of light. Anyway, that's an aside. So we've got the energy released in annihilation. You can also get a particle and antiparticle pair created. And this is called, because particles and antiparticles are always produced in pairs, this is called pair production. In fact, I'm going to rub out the word creation, and I'm just going to write pair production in here. Now, for this to happen, you need some energy to be converted into the mass of both particles. And that energy will be converted into a particle and an antiparticle pair, each with an energy E naught equal to its rest mass energy, which you get from the formula sheet, which is what we looked at the start. So all those masses we had at the beginning of this video, so the mass of an electron, 9.11 times 10 to the minus 31, those are all rest mass energies. Now, we've only got one photon coming in here. So for pair production, HF must be equal to 2 lots of m naught c squared. Whereas when we had annihilation, you had 2 photons produced. To aid the conservation of momentum, usually happens near a nucleus, because then the nucleus can recoil and carry off some of the momentum. So that's creation. Before we move on to the next section, there's a couple of bits that I forgot to put in the particles and antiparticles section. So every particle has its own antiparticle. So that means that protons have an antiproton, neutrons have an antineutron, and electrons have the anti-electron called the positron. Now you could draw or combine these to make, say, an anti-helium nucleus. That diagram I've got there at the start was of a helium nucleus there with 2 protons and 2 neutrons. So anti-helium would still have 2 antineutrons, which we write with a little bar across the top. but it would also have 2 antiprotons. Therefore, its nucleus would be negative. And surrounded it would be, just suddenly realised that's a really, really bad drawing, isn't it? We've got loads and loads of extra electrons. We should only have 2 electrons for helium, so let's just go through and re-rub out all of those. That was absolutely awful. There we go. And then we've got a couple of anti-electrons or positrons orbiting the anti-helium. We've also got antineutrinos, so we have an anti-electron neutrino, again written with a bar over the top. The positron isn't written with a bar over the top for some reason. We've got an anti-muon neutrino and an anti-tau neutrino, written like so. Now, there's a couple of other things as well that you should know. There's some experiments that are going on at the moment to look at, say, anti-helium and helium. Actually, it's anti-hydrogen and hydrogen because they're much easier to make. But they're looking at the energy levels and seeing if the energy levels are the same for matter and antimatter, which is really very exciting because in this pair production thing we've got here, we should have the same amount of matter. For every particle, we should have an antiparticle created. So same amount of matter plus antimatter is created every time. And the universe, as far as we can tell it, is all matter, or at least that we can observe. So that does beg the question, where has all the antimatter gone? And this is a very, very active area of research at the moment, and there's several collaborations at CERN looking at it. Finally, E equals mc squared is actually not on the syllabus. They save you the hassle of doing E equals mc squared, would you believe? So, if you have a look on the data and formula sheet, you can look up the masses not in kilos, but in mega electron volts. So you could say for a proton, use equals mc squared and go, oh, mass of a proton, mass of an electron rather, is 9.11 times 10 to the minus 31. And then we multiply that by c squared, 3 times 10 to the 8 squared, and then we divide it by 1.6 times 10 to the minus 19, and you could work out the energy that way, which is the rest mass energy. So for the rest mass energy. So the energy equivalent to the electron's mass, if you look it up on the formula sheet, is 0.510999 mega electron volts. Now, if you do that on your calculator, you won't get that answer. Instead, you'll get something that looks like, don't write this down, 0.512436. Now, the reason for that is that you're only using a 1 significant figure value for the speed of light and only using a 3 significant value for the mass of an electron. And they've given you a 2, 4, 6 significant figure value there. So if you want to get your answer to match theirs, you should go onto the internet and look up a 6 significant figure value for the speed of light and the mass of an electron. So all you'll have to do is look up the rest mass energies in mega electron volts on the formula sheet, and then you add up the total number of particles that you've annihilated, and that gives you the total energy, and then that will give you the energy of the photons that are released. So you don't actually need to use E equals mc squared at all. Anyway, that's the additional bit on particles and antiparticles that didn't end up in the previous chunk. So the next bit of the course was on forces. And there are 4 fundamental forces. That does not look like an N. Fundamental forces. Some of them are very familiar, like gravity, and some of them less so. So the strongest of the forces is the strong force, which you were introduced to back in lesson 3. And that's responsible for holding protons and neutrons together in the nucleus. There's a force called the weak force, and that's responsible for changing these things called quarks into other kinds of quarks. And again, we'll look at that in the next couple of lessons. Then there's electromagnetism, or EM. And finally, there's gravity, which is the weakest of the forces. So they are in order from strong to weak. Now, it turns out that you can treat these forces a bit like particles. So imagine that you had 2 people on ice skates with no friction at all, and one of them threw a, say, heavy thing like a basketball to the other one. As the first person threw the ball, let's just draw this. Again, don't write this down, I'm going to rub it out. But imagine here's person 1, and here's person 2, and this person throws the basketball in that direction. And conservation of momentum says that that person must therefore move backwards as they throw the ball. And then when this person catches it, the ball knocks into them and knocks them backwards. So you end up by passing this basketball between the 2 ice skates as they move apart. That's a really, really simplified analogy of the whole thing, but it turns out that you can treat these forces as passing that force in terms of particles. And these are called exchange particles. So, we need a heading on this table, which I haven't really left room for. Exchange particles. The exchange particle for the strong force is called the gluon, which is given a symbol little g. The weak force is W plus W minus, so W for weak, and Z naught, Z for 0, because it has no charge. The W plus is positive and the W minus is negative. So it's W particles and Z particles. Electromagnetism, well, a particle of electromagnetic radiation is the photon. It's given the symbol gamma. And finally, gravity is the graviton, which hasn't been detected yet. It's purely hypothetical. It should be given the symbol big G. Their range, well, we know the range of the strong force, which is about the order of 3 femtometers. Electromagnetism and gravity are infinite. And the weak interaction is somewhere in the region of 10 to the minus 16 or less of a meter. So very, very short ranged with that. So after we talked about the fundamental forces and their exchange particles, we then went on to look at drawing some of these interactions using Feynman diagrams. Feynman diagrams are a nice simple way of drawing particle interactions. And let's supposing for an example that we look at electron capture. I'm going to draw a number of these. Now in electron capture, an electron around the edge of an atom in the inner shell is captured by a proton in the nucleus. Now if you start off with a positive and a negative, you end up with a neutron particle called a neutron. Now, there's also something else, and that neutrino comes back in again. And because we've got an electron, it's going to be an electron neutrino. And that's how a proton can change into a neutron in the nucleus, or one of the ways. Now, we can draw that in the following way. Proton and electron. And the y-axis of this diagram is time. So as you move up the page, time is passing. So you don't ever have any arrows pointing downwards. Otherwise, it'd be going back in time. And for this interaction to take place, they pass one of these virtual particles across. And the proton changes into a neutron, and the electron changes into the neutrino. Now, what particle is it going to be? Well, we start off with a positive charge in the proton, and then we end up with a neutral charge in the neutron. So that means, where's the positive charge gone? Well, the positive charge has gone this way to be combined with the negative charge of the electron, and then we end up with a neutral neutrino. So the only positive exchange particle is the W+, so that's the W+. Now, if we go back all the way to the neutrino video, we could draw one of these things for beta decay. This time we only start with one particle, which is the neutron. And the neutron changes into a proton. And we've got another exchange particle. Now, we started off with neutral, and we end up with positive, so this particle must be negative. And the only negative exchange particle is W-. And that changes into the electron, or the beta particle, if you want to record it as a beta. Either is perfectly valid. And an anti-electron neutrino this time. We'll talk about why those things are anti-neutrinos and neutrinos in the last lesson. We could do a few other things as well. We could do a neutron-neutrino interaction, which is the reverse of the electron capture. Neutron-neutrino interaction. Now with that, we'd have a neutron plus an electron neutrino, and that will go to a proton and an electron. So that happens if you have too many neutrons in the nucleus rather than too many protons. So we start off with the neutron and the electron neutrino. Neutron changes into a proton. The neutrino changes into electron. So if we start off with neutral in the neutron and positive in the proton, then the negative charge has gone this way, and the neutral neutrino and the negative W- turn into the electron. So that's the neutron-neutrino interaction. As well as beta decay, you can have yet another decay. So we've got electron capture, neutron-neutrino interaction, and we can do the opposite of beta decay. And we can do beta plus decay. And a beta plus particle is a positive electron or positron. So what happens here? We start off with a proton this time instead of a neutron. The proton decays into a neutron and a positron. So if we want to get positive at the end in terms of positron, then we need to start with the positive proton. And there's a neutrino, and this time it's an electron neutrino rather than an electron antineutrino. And you would draw that like so. Start with the proton. Proton changes into a neutron, which changes into the positron, or you could write it as beta plus, and then neutrino. So if we started with positive charge and the neutron is neutral, then this exchange particle must be positive. So it has to be the W+. There's one other one that we could draw. These are all in the textbook. We could draw a proton antineutrino interaction. And the rules for why these are allowed interactions will come up in the final lesson. But for the moment, this is just how we draw them. So we start with a proton and an electron antineutrino with a bar above it. What will the proton change into? Well, it's going to change into a neutron. And the positive charge that was with the proton will go over here. And the antineutrino will change into a positron, which you've got positive charge, which is going to change into a positron. And you'd write that out, saying proton plus antineutrino goes to neutron plus positron. You don't draw this, but you should be able to see here that there are some similarities. We've taken the neutrino from there and put it on the other side as an antineutrino. So there are some patterns here that you should be able to spot, and you can see between here and here, we flipped it, and then where we started with an electron and an antineutrino, we now have an antineutrino and an anti-electron. So there are some patterns here that will all become clear in the final lesson. But those are Feynman diagrams. The next bit is a very, very large bit actually, and it's all on grouping particles, so there's quite a lot of new information here. So, grouping particles. And the first thing we need to introduce is something called quarks, which I'm going to put down here. So it turns out that protons and neutrons are not fundamental particles in the sense that they are not something that is indivisible. They are composed of, change colour to blue here, they are composed of three particles called quarks. So a proton has two what are called up quarks and a down quark, and a neutron has an up quark and two down quarks. And they have different charges, so we know the total charge on a proton is +1. The up quarks have a charge of +2/3, and the down quark, therefore, to end up with a charge of +1, must have a charge of -1/3. Two lots of 2/3 is 4/3 or 1/3. Take off a third, and you end up with +1. Ditto here, 2/3 minus a third minus another third gives you 0. The neutron is neutral. Now, they are never found on their own, as far as we know. Never found on their own. They always come in groups that add up to a whole amount of charge. So you can have a total charge of +1, +2, -1, or 0. So using that rule, we can go away and try and create, if you're doing this on paper, you should use a ruler for this bit. We can go away and see how many particles we can create. Now, there are 6 quarks in total. There's up, down, and strange, which you need to know about. But there are also charm, top, and bottom, which you don't need to know about. So let's put some lines through those. But I include it for completeness. Now, as we've said, an up quark has a charge of +2/3, and a down quark has a charge of -1/3. Now, a strange quark also has a charge of -1/3, which you need to know, and it's on the formula sheet, that information. However, it may not surprise you to see that the charm and the top quarks have charges of +2/3, and the bottom quark has a charge of -1/3. In other words, they come in pairs. Now, What you should do now is pause the PowerPoint and have a go at making up as many particles that you can using those 3 quarks, which have a total charge of +1, +2, 0, or -1. They have a whole amount of charge. So I would pause the PowerPoint here and see how many you can make. Okay, so particles that are composed of quarks are called hadrons. Now, there are 2 ways of making hadrons, or, well, if you've been putting them together, you should have found there are 2 distinct groups. There are baryons, which have 3 quarks, like our proton and neutron. So let's start with those. We've got up, up, down, which we said was the proton. We've got up, down, down, which is the neutron, +2/3, -1/3, -1/3. You could also have up, 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 down, 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 and strange, strange, strange. Now, you don't need to know, you need to know what the proton is, you need to know what the neutron is, but you don't need to know any of the others. But for completeness, I'm going to put their names down, but I'll change colour to, what should we have? Grey. So you don't need to know that. These 2 are deltas, and the 3 stranges is called an omega particle. It's minus. You do need to know what the charges are though. So if you had 3 up quarks, you need to know that 3 lots of +2/3 gives you a total charge of +2. You could also have particles with 1 strange quark in. So you could have up, up strange, up, down strange, and down, down strange. Now, these are all sigma particles, and they do tend to appear in the exam, not because you have to remember what a sigma particle is, but they do like to say something on the lines of, a sigma particle has a strangeness of -1, for example, and a total charge of plus. Work out its quark combination. So you would have to work it out using the rules, and if you know what they are, it might help you in the exam. And then you might go, oh yes, no, that's right, it should have a strange quark in, it might speed the process up a little bit. So up, up, and strange, +2/3, +2/3, -1/3, that's a total charge of +1, so that's a sigma plus. +2/3 for an up, -1/3 for a down, -1/3 for a strange, that's 0. And down, down strange is 3 lots of -1/3, so that's a sigma minus particle. Again, you don't need to know these, I include them for completeness. And the other 2 that you could make with 3 quarks is up, strange, strange, and down, strange, strange. And these are called Xi particles. And up, strange, strange is a total charge of 0. And down, strange, strange has a total charge of -. So those are the particles with 2 strange quarks in. So what you need to remember is that protons and neutrons are not strange. So have no strange quarks. Now, there's also the antibaryons, of course, which have 3 antiquarks. So we could put all of these anti-up, anti-up, anti-down is the antiproton, and anti-up, anti-down is the anti-neutron. And you could go through and make all the other antiparticles as well, which we won't bother doing now. The other way of making hadrons is by putting a quark and an antiquark together. Let's draw a line down here. Now, again, there are a certain number of ways you can do this. You can have particles that are not strange, which are called pions. And you can have particles that are strange, called kaons. So how can you make, let's say, a positive pion, a negative pion, and a neutral pion? Well, the positive pion, up, anti, down, would give you a total charge of +1 without a strange quark. Anti, up, and down gives you the pi minus, -2/3. Oh, what we haven't done, if we have the anti-up and the anti-down, remember that anti-quarks have the opposite charge, but the same size charge. So an anti-up has a charge of -2/3. Anti-strange, anti-charm, anti-top, and anti-bottom. Sometimes top and bottom are called, you might see them referred to as truth and beauty. So if you ever see those phrases, that's what they're referring to. Again, these things are not on the syllabus, so just put some lines through them, but it follows the same pattern. Pi 0 could be up, anti-up, down, anti-down, or strange, anti-strange. Now the strangeness of the strange and the anti-strange cancels out, so it's not strange. So that's why it's in the pion section. Kaons are given, unsurprisingly, the symbol K. So we've got a K plus, a K0, oh, sorry, a K minus. And there are two K0s. One's a K0, one's an anti-K0, and I can never remember which way around they are. But in the exam, they will tell you. So you can have down, strange, anti-strange, or strange, anti-down. And what it might say in the exam is a K0 has a strangeness of blah, 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 work out its quark combination. Then you'd know whether it was a strange quark or an anti-strange quark. So that's the particles composed of quarks. So we've got mesons and baryons and antibaryons. Those are all hadrons. Now, protons and neutrons experience the strong force. And in fact, all things composed of quarks experience the strong force. But there's other types of particles as well. So the other main group of particles is the leptons. And again, they fall into three families. So like the quarks, we've got three families. We've got the electron, and the electron comes with an with a electron neutrino. Okay. But from the video on neutrinos, you know there are in fact three types of neutrinos. And there are also three leptons. So the electron is the first family, that goes with the up and the down quarks, which form protons and neutrons. Then you've got the muon, which is heavier than the electron, and that's the second generation, which goes with the charm and the strange. And you've got the tau, which is the third, and that goes with the top and the bottom. So you've got these three families for some reason, and their corresponding neutrinos. They've all got a charge of -1. And of course, they have their corresponding antiparticles. So we've got, now these are not written with bars. So we've got the E plus, the mu plus, and the tau plus. So that's the positron, the anti-electron. And then you've got the anti-muon and the anti-tau. And they have, again, their corresponding anti-neutrinos. Now these are written with bars. Like so. There's one other thing that doesn't fall into any of this, which is a separate category, all on its own, which is the Higgs boson. So that doesn't fall into any of those categories at all. And the only other particles that there are that you need to know about are the four force carrier particles, virtual particles. So gluons, I say four particles, W plus, W minus, and Z naught for forces. the photon and the graviton. In reality, there's a lot more particles you could make if you included the 3 quarks and the 3 antiquarks that you don't need to know about on the course. But it gives you almost a complete picture. And when they found all these particles, before they managed to group them like this, it was all very confusing and nobody really knew what was going on. They said, who ordered these particles? And they called it the particle zoo. Those are particles that didn't seem to fit together. So the final bit of the course is on conservation laws. So here we go. Which tries to make sense of some of these particle interactions like beta decay and explain why you have an antineutrino instead of a neutrino. So to do this, we need to introduce some quantities. So we know that charge is always conserved. This is not new. So if you start off with 2 particles with a total charge of +1, so one is positive, one is neutral, then at the end you must end up with 2 charges, or sorry, a total charge of +1. So you could have 1 positive charge and have many neutral particles, or you could have 2 positively charged particles, a negatively charged particle, and however many neutral particles, but the total charge before and after must be the same. We also know that energy and momentum must be conserved, because that's why we get those 2 photons produced in annihilation from earlier. But there are a few other quantities as well. So, baryon number must be conserved. And then so baryon number, baryons have a baryon number of +1. Antibaryons are not, antibaryons have a baryon number of -1, which makes sense because if you bring, say, a proton and an antiproton together, they annihilate, and then you have no baryon. So something that's not a baryon, like nothing, e.g. energy, has a baryon number of 0. But also leptons have baryon numbers of 0 as well. So that's baryon number. We also have lepton number, which is basically the same thing but for leptons. So leptons have a lepton number of +1. Antileptons have a lepton number of -1. So these numbers here are lepton numbers. These numbers above are baryon numbers. And therefore, not a lepton, that's all baryons and exchange particles, have a lepton number of 0. Now finally, strangeness. Anything with a strange quark in it has a strangeness of not +1 as you would think, but a strangeness of -1. And anything with a strange antiquark in has a strangeness of +1. So we should do some examples of this. E.g., let's take our sigma minus particle, strange, 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 has a strangeness of -1, -1, -1. Total strangeness is -3. Our sigma, say sigma 0, will also have a strangeness. So our sigma naught is up, down, strange, which has a strangeness of -1. Not to be confused with a charge of 0. So don't get these different quantities confused. Now what we really need to do is to go back to the Feynman diagrams and work through some examples of these. So if we come back over here, and we're not going to have space to do it with electron capture, but we'll start with the neutron-neutrino interaction. So let's look at charge before and after. So if we write out the interaction first, so we've got a neutron and an electron neutrino before, and afterwards we have a proton and an electron. So charge. Beforehand we've got a charge of 0 for the neutron, 0 for the electron neutrino, +1 for the proton, and -1 for the electron. So the total charge before is 0, total charge after is 0. It's conserved. If we look at baryon number, a neutron is composed of 3 quarks. It's a baryon, so it's got a baryon number of +1. A neutrino is a lepton, so it doesn't. Proton is also a baryon, and electron is not a baryon. So we have a baryon before and a baryon after. Brilliant, it's conserved. Lepton number, we've got neutron is not a lepton, but a neutrino is. Proton not a lepton, but an electron is. And again, that's conserved. We've got a lepton before and a lepton afterwards. And finally, strangeness. None of those particles are strange, so strangeness is conserved. Now, strangeness is always conserved in the strong. We should make a note of this over here. So it's conserved in the strong interaction, but it's not necessarily conserved in the weak interaction. For reasons that I will explain in a couple of minutes. So that's our neutron-neutrino interaction. We can do the same thing for our, let's do proton-antineutrino. So we've got proton plus antineutrino goes to neutron plus positron. So charge, proton has a charge of +1, antineutrino is neutral, neutron is neutral, positron charge of +1, so charge is conserved. +1 before, +1 after. Baryon number, proton is a baryon, so it's got a baryon number of 1. That's a lepton, that's a baryon, that's a lepton, so that's conserved. Lepton number, well, now our antineutrino has a lepton number of -1, and our anti-electron, the positron, is an anti-lepton, so that has a lepton number of -1 as well, which is why this has to be an antineutrino and not a neutrino. We started off with an anti-lepton before, and we had to finish with an anti-lepton afterwards. None of these are strange, so strangeness is conserved in this interaction. We might well actually just have enough space to do under here the two at the top. So let's do this one here, so electron capture. So here we've got an electron plus a proton goes to a neutron plus a neutrino. Before and after. So we've got charge, -1, +1, 0, 0, that's conserved. Baryon number, 0, +1 for the proton, +1 for the neutron, 0. Lepton number, +1, 0, 0, +1. So you can now start to see why we have to have a neutrino or an antineutrino. It has to balance. We have to have the same lepton number before and after. And again, strangeness in all of these examples happens to be conserved. We'll do an example where it's not in a couple of minutes. We'll do beta plus decay down here. So here we've got a proton going to a neutron, a positron, and a neutrino. So charge, +1, 0, +1, 0, that's conserved. Baryon number, we started with a proton, which is a baryon. We finished with a neutron, which is a baryon. So that's conserved. Lepton number, proton and neutron are not leptons, they are hadrons. And then we've got -1 for the positron, and therefore we must have a neutrino, a particle with a lepton number of +1 to balance it out. So that is now conserved, and that's why that has to be a neutrino or not an antineutrino. Strangeness is 0 in all of those cases, and for completeness we'll just go back over here and we'll do beta decay as well. So neutron to a proton plus an electron plus an antineutrino, and by now hopefully you can start to see why that's going to be an antineutrino. So that's got a charge of 0, +1, -1, and 0. Conserved. Baryon number +1, +1, 0, 0. That's conserved. Lepton number, those are both baryons. This is a lepton, and therefore we need an antilepton because we didn't have a lepton beforehand. So lepton number must be 0 afterwards. So we need an antilepton. Strangeness is 0. And a lot of people get a bit confused with what baryon number and lepton number and strangeness mean. They are just numbers that allow you to predict what can and can't happen. We know that the number of baryons before and after must stay the same. And that allows us to predict which of these interactions are actually allowed to happen. Now, I'll do a couple more examples, and I'm rather hoping I might be able to find some space somewhere. It's going to have to be over here, I think. So let's just do a couple more interactions. We're not going to draw Feynman diagrams for these because the Feynman diagrams are a lot more complicated for more complicated interactions. But let's imagine that we had 2 protons colliding. And then, say in the Large Hadron Collider. So they've got a lot of kinetic energy, and Einstein equals mc² says you convert kinetic energy into mass. So we can create some new particles. So we end up with a proton, a neutron, and a pi plus particle. Let's just have a think about what's going on here by looking at the quark combination. So we've got up, up, down, up, up, down, up, up, down, up, down, down, and up, anti-down. So we've got a proton before and after. We've got 2 up quarks before and after, and 1 down quark. So the new stuff on this side is a down and anti-down pair, which has been created through pair production. So we've had no quarks changing into other quarks. We've just got a quark and anti-quark pair created, and then they've moved around. You've changed the combinations. You've put the down quark in place of one of the up quarks, and that up quark is paired off with a down quark. So, whoops. So this is the strong force, because there's no quarks changing to other kinds of quarks. It's just a reshuffling. So let's just do the conservation laws on this. We've got charge of +1, +1, +1, 0, +1. So total charge is conserved. That's really good. Baryon number. We've got a proton, which is a baryon, a proton, which is a baryon, another proton, and a neutron, which is a baryon, and a pion, which is not a baryon. So if you think about it, back over to here, so mesons oh, we should put quarks in here. So quarks have a baryon number of +1/3 because 3 quarks make up a baryon, so 3 lots of +1/3 make a whole +1, baryon number of +1. So therefore mesons have a quark and an antiquark, which is a baryon number of +1/3, and an antiquark will have a baryon number of -1/3. giving a total baryon number of 0. Mesons are not baryons. They fall into another category, rather obviously. So that's why our meson has a baryon number of 0. Lepton numbers, there are no leptons involved in this interaction at all. Leptons do not experience the strong force, but they do experience the weak. As you can see from all of these Feynman diagrams here, which all involve leptons and all involve the W particle. And strangeness is 0, 0, 0 across the board. Right, so let's do another example. Let's imagine that we've got a negative pion, a pi minus, and a proton, and you fire them together and you end up with a K plus and a sigma minus particle. Now they might at this point ask you to work out what that final particle is. So for example, they would expect you to know that this is going to be an anti-up and a down. Your proton's up, up, down, and your kaon is up, anti-strange. And they say, well, what's left over here? They wouldn't expect you to know the quark combination of a sigma minus. They'd expect you to go, well, we've got an anti-up and an up. Those will cancel. We've got the up is here, leaving us with two downs, which haven't gone anywhere. And if we've created an anti-strange, we must create a strange alongside it. So this is our pair production. And they expect you to be able to work that out. But like like I said, if you know that a sigma particle has a strange quark in it, all sigma particles have a strange quark, sigma for Greek letter S, S for strange. And then that makes that particular question a lot easier. Now, what force is this? Well, no quark has changed into another kind of quark. We've annihilated some, we've created some, but all we've done once those annihilations and creations have happened is move them around. So this is also the strong force going on here. There are no leptons involved here at all. So conservation laws, -1, +1 beforehand, +1 and -1 afterwards. That works. And this is a good check if you've ever tried to make a particle at the end. You can go through and check that it's got the right charge and things. Baryon number. Well, the pion and the kaon are both mesons. They're not baryons. So that third particle at the end must be a baryon, which it is. It's a sigma particle. Lepton number. None of these are leptons. So lepton number's conserved, as is baryon number and charge. Now, strangeness here, as we've said in the strong interaction, strangeness is always conserved. So 0, 0. But now we've got an anti-strange quark. Remember, the anti-strange quark has a strangeness of +1, and the strange quark has a strangeness of -1. It's the opposite way around to what you think it is strange. So strangeness here is conserved in the strong interaction. Let's do an example where it's not conserved. So let's imagine that we had a K plus meson decaying into two pi plus mesons and a pi minus meson. Well, let's have a look at what's going on with the quarks here. So our K plus must have a strange quark or strange anti-quark in it. So it's going to be up and anti-strange to make a total charge of +1, but the pions have no strange quarks in at all. So this is up, anti-down, up, anti-down, down, anti-up. So an up and an anti-up have been created, a down and anti-down have been created, and we started with an up, which has gone here. So essentially we have converted an anti-strange into an anti-down. In reality, it's a bit more complicated than that, but for the moment, this is a good way of thinking about it, I think. So if we've changed one quark into another, it must be the weak force. And strangely, this is not conserved in the weak force, as you should be able to see, but we'll show now. So let's just do charge, +1, +1, +1, and -1. So total charge of +1 before, total charge of +1, because the plus and the minus cancel afterwards. Baryon number. None of these are baryons, they are all mesons, so baryon number is conserved. Lepton number. None of these are leptons, so that's all conserved. Now strangeness. We started with an anti-strange quark, so strangeness of +1. But we don't have any strange quarks afterwards. Why? Because we have converted a strange quark into something else. And if you change the strange quark into something else that's not strange, clearly strangeness cannot be conserved. And this is why these particles were called strange. So strange particles are created in the strong force. So this is where we created the strange particles. Strange particles created with the strong force, but decay through the weak force. And normally, particles that are created through the strong force decay through the strong force. The quarks just reshuffle in another combination and you end up with a different particle. And normally particles like electrons that are created through the weak force decay via the weak force. So this was really, really odd behavior when they first discovered it. And that's why they called these particles strange and invented this, what we call a quantum number, this strangeness value to describe that. There's another example I'd like to do here. Sorry if you've run out of space on your piece of paper. So let's look at leptons, and let's look at muons. I think this is quite important. So the muon is the heavy electron, and it decays into an electron. Now, on first sight, that looks perfectly plausible. I'm just going to move that across a little bit to give myself a bit more space. We've got charge of -1 and -1. We've got baryon number seems to be conserved. Lepton number seems to be conserved. Both leptons. And strangeness for completeness, as it doesn't involve any strange quarks, there's no hadrons at all, we're not going to have any strangeness involved at all. However, that's not the complete picture. We have two neutrinos involved in this, because lepton number is split up into lepton number and muon lepton number. So we're just going to have another go at this. That's fine because they don't have any charge and they're not baryons. So baryon number and charge are still conserved. Now, this is not an electron, so it has an electron lepton number of 0. That is an electron lepton. It's a positive lepton. It is an lepton rather than anti-lepton. So then we need an anti-electron neutrino to balance it out. And that's not an electron neutrino, so that has an electron lepton number of 0. So that's conserved. This is a muon, so that's a particle. Those are leptons, but they're not muon flavored. And so we've have to have a muon neutrino to balance the muon on the other side, whereas here we need an electron antineutrino to balance the electron because they're both on the same side. So that is an example of a lepton decaying. And this will be the weak force. And although you don't need to know this, you could draw the Feynman diagram as so. Start with your muon. That changes into a muon neutrino. Then we end up with the electron and the electron antineutrino here. And because we started with a negative charge and it's gone this way, that must be a W minus. So that would be an example of the Feynman diagram for that interaction. Notice it's still the weak force, even though there's no quarks involved, changing into other kinds of quarks. But it's still involved with converting leptons. There's one other thing that we need to talk about. Sorry, this is all kind of a little bit of an itty-bitty last finish off here. And that is going back to our fundamental forces. Now, the gluons work between quarks, but they cannot reach over longer distances between the individual protons and neutrons. So we might have gluons drawn as little spirals acting between the quarks, holding them together into protons and neutrons. But what happens is that these gluons turn into a particle-antiparticle pair, a pion, which then travels to the proton because that's longer lived than the gluon. And then that then changes, that's how they exert a force between the protons and the neutrons. It's a bit complicated, but there's a really lovely animation on Wikipedia if you go and look up the strong force. So the gluons work between the quarks, but the pions, pi naughts, act as the exchange particle between the protons and neutrons, and in fact between baryons. And you need to know that as well. You'll be very glad to know that is it for particles.